I'm thrilled to have Titus Murray from Southern Highlands Structural Geology here with us today. Titus is a structural geologist with extensive experience in the study and characterization of faulted and fractured aquifers and reservoirs in over 30 countries. And today he'll be giving us an introduction to seismic structural geology. So it's going to be a great session. Please use the chat. You'll have the chance to jump off mute and we'll have some discussions at the end of the presentation. And yeah, thank you so much, Titus, for joining us. It's awesome having you here.
No worries, Jess. It's a lot of fun putting this stuff together.
Yeah.
So I guess I should be really saying thanks. There's a customer who's spurred me to put this together through COVID. So I can't say who they are, but so thank you anyway, because they made me think about this. This is sort of some stuff I put together for them. Anyway, so I'm going to go through and talk about seismic and how we can think about using seismic in different ways in structural geology. If you've used seismic a lot, this might be a bit boring, but these are sort of some of the tricks and ideas that we've been putting together on how we can move the use of seismic across into different areas. So just to start out, can you just draw yourself a fault? Just get a pencil and paper and draw yourself a fault using 3 lines. Pretend you're talking to an accountant and you're going to draw a fault, and just draw that quickly. So it shouldn't take long. You can draw it on a pencil and paper. You can get sand and you can use a stick and you can draw it. It's that sort of thing. So what did you end up drawing? And there's sort of 3 end members that you can get to here. You can draw yourself a fault like this, a normal fault, or you can draw yourself a reverse fault. How many of you drew those? Or you can end up drawing a fault like this with a vertical fault. So what I've seen from working with a whole range of geoscientists around the world is that there's a bit of a cultural basis to this. Normal faults, I see loads in Australia. I see lots in Holland. Lots in the North Sea. Norwegians in particular. The Norwegians, it's like they've got a piece of glass and they've dropped it on the ground and they end up with these shattered maps of faults. These strike-slip faults, which are the steep ones, you'll often see from the Dutch geoscientists and anyone who's gone to Stanford because they went to university on a strike-slip fault. And reverse faults, I really see them from Colombian geologists and Canadian geologists. So right from time zero, as we're doing our interpretation, we're thinking about faults, we're actually bringing a bias of what we've seen or how we've been taught. And one of the real things I try and do when I'm doing seismic interpretation is break down that bias and try and get back to first principles. So excuse me if I go through some really basic first principles. Anyway, seismic. Basically with seismic, all we're doing is we're putting sound into the ground and we're looking at how that sound wave moves through the ground. It moves faster through rock than it does through air. And yeah, if we're up in space, the sound just doesn't move at all. And so really that's what we're looking at. And we're just using sound to explore the subsurface. We can put sound into the ground all sorts of different ways. The easy way to do it is the hammer. This is the largest vibro-sized truck in the world. It's sort of 90 tons, and it sits there with a big hydraulic ram vibrating the ground. And it's amazing. Put a pile of energy into the ground. A lot of the stuff that we'll end up working with is in fold and thrust belts, and that's where dynamite comes in. And there's nothing better than blasting things, but it's great because you can move dynamite around really easily. So in PNG, there's a lot of work I've done with the guys at a company called Oilmin, and this is what the seismic lines look like. They're literally cut through the jungle and they can use dynamite in that, and it's a fantastic source in that respect. The one I really like is this typical American solution. If you can't solve it with a big gun, it just can't be solved. Just get a big 50 cal, put it on the back of your ute, and away you go, and that gives you a good energy source. So energy, all sorts of different energy sources. Really what we're doing is putting energy into the ground, and we're using a microphone, but it's not really a microphone. It's similar. Instead of having a membrane moving backwards and forwards, we've got a magnetic, we've got a spike into the ground that moves up and down, and an inertial mass, and that's what measures the vibration. This is a really cool geophone that I actually have at home. This is actually a little Raspberry Pi geophone. They're great. Not making anything, but it's called Raspberry Shake, and you can measure your own earthquakes. And that's literally, you can see inside here, you've got yourself this little inertial mass, and that's what bounces up and down. And so it's a really simple one. What they actually look like in the field is they look like this. People who put them in the ground are called juggies because they're called geophones and jugs, and they measure the vibrations. Really, all we're doing is we're looking at how that sound wave moves through the rock. We've got the wave motion, we've got an amplitude sitting in here. And fundamentally, the thing that we're using is we're using the fact that the rocks have different velocities. Now, I brought myself a source. We all have a source here. And here is some 11,000-year-old, last ice age deposit from Thermal Lakes. And you can hear if I put it in my microphone, we don't get much sound. Yeah, get me some Robertson basalt, and we get a much louder sound. We get much more of a ring. And in my local area, this is some of the Wongawilli seam. This is what Hume Cole wanted to send off to Korea to turn into steel. And you can see it's got a really different velocity. And what we can use is we can use these different velocities along in here from air through to these ultramafic rocks to get a sense of how the structure is all set up. And it's really just Wiley's equation. It's a reduction in porosity that drives the whole thing. Now, I'm going to cheat a bit. The sound waves are like you throw a pebble into the pond and you see the circle come out. Well, in fact, what we do is we simplify it out to ray paths. So if these are my pebble, these are my wave fronts, I can just use this ray path instead. So it's an approximation, but it really helps when you try and imagine this stuff. And what I'd like you to be able to do is imagine these sound waves, because as a structural geologist, we can help the geophysicist understand where the different velocity rocks are. And if we think in ray paths, then we can really help them process the seismic better. And that's what I've spent a lot of time doing over the last few years in particular. So the idea is in the simplest case, we have a borehole. We put some geophones, often they're actually hydrophones because they're in the mud, down the borehole. We have some sound out on the surface, and we can see how these ray paths move down, bounce, and come back into the geophone in the borehole. And that gets us a one-dimensional seismic survey. And that's a really useful one to get straight off, because then you've reduced your uncertainty. More commonly, the ones that I end up spending a lot of time, especially long regional ones, are 2D seismic sections. And there we have a source moving along the line with a whole set of receivers spread around there. So the source will leapfrog along. And that's the most common one. The one that's fantastic and that's really made a difference has been 3D seismic. 3D seismic, what we're doing is we've got a source and then we've got a whole array of receivers. And by using that array of receivers, we can actually start to we can understand the anisotropy in the sound waves as well. And that's brilliant. But, it's easy if you're offshore because you just get a boat, ship, go out there and you can go and collect it. If you're onshore, then it becomes more expensive, but it is doable. And getting that wider range of different angles makes a huge difference. Now, there is magic. Like, there's a trick to all of this. And you can see this Horatio Bosch one. Yeah, there's the magician, sleight of hand, and somebody's picking his pocket. Well, I'm not going to pick your pocket, but there is a bit of a sleight of hand here. There's a real trick to how this gets done. And what we're doing, wrong way. What we're doing is we're saying, okay, well, I've got a shot point here and the sound let off. There's my right wave and it comes through to the geophone. That gives me one shot of that common point. If I then move my source along, I can get another snap at this thing to another geophone. And I keep moving this along and I can move along. And I've now got 3 different samples of that one point. And the trick to all of this is you stack that information together. You can drag that information together so that you get this theoretical, what happens if I had an explosion where my geophone is. So it's going, effectively what I'm able to do is stack together those wave paths to that vertical common midpoint or common data point. And that's the real beauty of this, especially if you do it in 3 dimensions, is we can actually stack that information around. Now, you don't need to know all about this, but this is the stuff I find really useful to ask the really stupid questions of my geophysicist, because that's what we're at, where you're not going to be experts on geophysics, and I'm not an expert, but I know how to ask the tricky questions. And that's what I try and do with all of this. So effectively what we've got then is we've got this one-dimensional trace, sound comes down, bounces off something and comes back up. And so that's one-way travel time and then two-way travel time. And we keep stacking this up until we have a vertical trace of two-way travel time. It's just the way it is. We always report back in two-way travel time. So my half a millisecond becomes 1 millisecond, 1.5 becomes 3, etc., etc. So that's my stack of information that's been stacked together. And if I know something about the rocks, and this is where we come as geologists, because the geophysicists know about the sound and the electrons, all that sort of stuff, and the processing, we come and tell them what the rocks are and how hard they are, how they were deposited. And this is the real beauty of where we work together. We can then pull that together and give that a velocity. And each of those things we can say, well, that's faster, slower, softer, harder. If we know that, then we can start to say, well, we can get this idea of impedance. Am I going from slow to fast or fast to slow? And from that, that gets us a reflectivity. And ahead of time, we can get this idea of what we expect the peaks and troughs of the reflections to be like. That's broadly what we're doing is we're trying to work out what these sound waves will bounce off each of the layers. And we just do it lots of times. We do it loads and loads and loads and loads of times. And each one of these single things is a stack of fan of them coming together. And then we just step across the country, all in 3 dimensions, making a stack of these individual traces. Relatively straightforward. And we're just relying on velocity contrast. So that's what a seismic section looks like. You can see it's just a stack of these individual traces. And there's a whole range of ways you can get them to look at, and depends on the software you're using. Early on, they were just line graphs, literally using a line plotter. And then there was line graphs where you'd fill in the positive peaks to be thicker. And this is, again, is a display that still works really, really well as a way of trying to work out what you've got. Colors work well, and you can superimpose the traces and the colors. So depending on if you're looking at a report or you're looking from one of the surveys, you'll end up with these different trace images. So you're looking at something now, right? And you're starting to think about it. Well, what are you looking at? Now, just a little bit of a mind game. We've got ourselves a chessboard here, and we've got ourselves a green pillar. Square A, square B. Who thinks they're the same color? They're different colors, aren't they? But what the artist has done is they've tricked you. What they've done is they've actually gone through and played with the shading either side of A and B, and A and B are actually the same color. Our brain is sitting there going, okay, well, how does this work? You can see in this line in here, I've joined between A and B. That is the same color between them. And your brain's going, yeah, I know it's a chessboard and I know I've got a shadow. But the artist has actually tricked us. And the way we look at stuff really makes a difference on how we interpret. And we have to be quite quantitative a lot of the time, especially when we start looking at these colors and looking at all these squiggles. So it's super important to start to think about how you're doing that. The thing that really gets us from two-way time to depth, this is where we can start to really understand what our geometries look like. And really all we do to get from two-way time to depth is we divide it by 2000 milliseconds to seconds, and we get to velocity. It's, especially you guys, you're likely to be dealing with legacy seismic. It could have been recorded in Sumerian cubits. Sometimes it's in feet and seconds, sometimes it's in yards and seconds, sometimes it's in Clark yards and milliseconds. So the units you have to chase around the whole time, and it's a bit of a pain, but it's just legacy data. And effectively what we can do is if we've got a set of velocities, we can work out how from that two-way time, that gets us depth, and we can build up a stack, and we can stack our way. We can go down through the stack of sediments and work out how fast each of these things are and what our elevation is. And where this becomes really important is, here's a forward model. So this is taking a forward model geology with a fault, with a nice reverse fault in here. And because we've thrust this high velocity layer on top of this soft one, if I take it to time, you can see I've actually generated an anticline in here. and that anticline is purely in the time. It's not real. So you're looking at it and you think, yeah, it really makes a lot of sense, but you need to take it through depth to make sure you haven't done like those squares and said, well, those two things are separate colors when they are actually the same. So this converting to depth is super important. There's a great paper. Simon Stewart did this. He's now chief geologist at Saudi Aramco. He's an exceptionally good geologist. It's a really good paper to go and have a look at. What he does is he looks at different scientific papers and how often people get sections with one-to-one vertical exaggeration. Now, you guys all know this because you draw cross sections one-to-one. When you get into seismic, you're going to have to remember to do that. Drawing the sections one-to-one is really, really important. So he used a piece of software Move to do this. He took a section in here with some salt, and the salt's got really distinct velocities. He's then taken that depth section and converted to time, and you can see these anomalies in here are velocity anomalies. And then what he's done is he's shown it different vertical exaggerations. And it's really, really common to see time-based data with 4 times vertical exaggeration. You can see how different that looks to this. This is get a copy of this paper. It's open access, and just force it down everyone's throats. Tell them they need to work in time, they need to work in depth and get their vertical exaggerations right. Because we knew how to do this. Like this is the front of Lyell's, Principles of Geology. This is the front cartoon in the American edition here. And he knew how to draw a cross section. And for some reason, we've forgotten how to do that. And if you can draw a good geologic cross section, you can do a good seismic interpretation. So how I start with my seismic interpretations is I start to go and look at cataloging features. This is something from the Niger Delta. There's something called the Virtual Seismic Atlas that the guys at Aberdeen Uni have put together. Rob Butler. It's lacking money just now, but you can get into it. And I just go and catalog the features. There's a bunch of cross sections through the Niger Delta like this that are fantastic. I use them a lot to get ideas. And what Rob's done in here is he's gone and put in here's my anticline, here is gas and mud. So it's a ductile substrate. So it's a overpressured mud substrate, and you get mud volcanoes and these amazing anticlines forming. Synkinematic strata. These are listostromes. So he's just gone through and cataloged the basic geologic features in here. That's my starting point to try and understand those. Now, we're going to spend a lot of time trying to understand where we can get faults and what is a fault. And you can see here, I've just done, there's this issue of resolvability. What can I see and what can't I see? So I've had 2 points and I can see that they're a long way apart, then I can resolve them. And the closer and closer they get, the lower the harder it is to resolve their 2 points. And the same with the faults. That's definitely a fault. And you can see as I get through this section, there's less and less likely to be a fault. In fact, it goes the other way. Now, just a quick example for that. Now, if I change that and I put some noise in behind it, you can see it's really hard in this red zone to work out whether I've got a fault or not. So this resolvability is a real bugbear when you're dealing with seismic, knowing where you have and haven't got a fault. And so I really like to go through and catalog places where I know I don't have faults and look for areas of flat lying areas and say, well, I know that's not faulted, and then start to look at those dip panels. And especially when I'm dealing with dodgy fold and thrust belt onshore old seismic. Here's a really nice section from the guys at Total Depth. You can see a bunch of faults through here. What they've done is they've used an automatic picking process, and this is what I do by hand, and they've gone through and automatically picked them. Now, if we have a look at that, you can say, oh, well, there are my faults. There's a fault there. I can see if I've got a fault here. But when you're picking a fault, you're actually picking the absence of a coherent reflector. You can see that's nice and coherent in there, and then we lose coherence, and that's where we're picking the fault. And it's a really interesting one because what we're doing is we are invoking a fault in the lack of coherence. Mondrian is a Dutch painter, and he's famous for these. You see these sort of diagrams, these sort of paintings all the way through Holland, the Netherlands. And he started out painting trees. Instead of painting trees and painting the twigs and the branches and the leaves. He actually painted trees in wintertime. He painted the sky behind the tree. He painted the negative space. And so this is a progression of his work from his early ones painting the negative space and these trees becoming more and more. You see this blue one in particular. He's really painted the sky behind the tree, and the tree is the black. And that's what evolved to these things where he's exploring negative space, and then finally to his more abstract. So if you were a bird and you're being chased, a little bird being chased by a hawk, you'd see a tree and you'd see all the holes you can get through it. But as humans, we just see the tree as this big mass. Now, when we're looking at faults, we have to flip our head around and we have to think about that negative space. And so when we look at that, I'm looking at where we don't have coherent reflectors. Super important to make sure we use sensible naming when we're doing all this stuff. It's really hard actually to find this information. Dave Peacock's diagram, this is a beautiful diagram. It's just a glossary of fault terms. I always keep in my field vest. I always keep Ken McClay's little handbook on structural mapping. It's great. He goes through distills a lot of his stuff from his glossary of structural terms into here. And it just means then that we're all using the same terms. So when you're talking to the geophysicists, you're using a consistent terminology. I find it really helps. So when, again, stuff from Virtual Seismic Atlas, you can see that Rob's gone through and used a systematic sense of describing these sorts of features. Now, we've known how to draw good cross sections for a long time, and a lot of this, when you're interpreting seismic, is drawing cross sections. So this is Strachey's first. This is one of the first recorded cross sections. It's in the Geolsoc. William Smith stole it and put it in his notebook, and this is him trying to work out whether this coal mine, which he owned, was connected to that coal mine, and he drew this cross section. It's a really good quality cross section. This was the first time. Now, evidently, people have been doing this. William Smith kept on with the idea, and his map, if you ever get to London, go to the Geolsoc, it's just knock on the door and go and have a look at the map. It is absolutely stunning. And his maps and cross sections for England are fantastic. Really nice. This guy Wigley in the last 10, 15 years has gone through and tied the seismic now through the Wheel Basin here to William Smith's cross sections, and his cross sections tie with the seismic. Now, a lot of the time you'll find that geophysicists don't tie the outcrop geology to the seismic. That's what you're meant to do as geologists. So this business about tying the outcrop geology to the seismic is super valuable and super useful. And the reason you're doing this is what you're going to try and do is develop one of these, which is a geologic cross-section of velocity. Because if you can draw a geologic cross-section of the velocities, then it's amazing what the geophysicists can produce. And that's a lot of what I spend my time trying to do, is how do I draw a really good geologic cross-section of velocity rather than porosity or gold equivalent or whatever. So part of that is understanding just going back to basics of geology, and effectively there's the law of superposition, and it's a last in, first out. It's a LIFO system. If I want to get that plate, I need to take all of these off. If I go and get my milk, it's actually a FIFO system. It's first in, first out. They have these, but you can get in there behind and the milk goes down the front and you get the oldest milk first. Now in geology, it's like this, not like your milk at Woolworths. And effectively this stack is younger and younger things sitting on top of it. Now, obviously we've got intruders, but that law of superposition is a really important one to make sure we include in it. And as you're thinking about what thicknesses and materials are going in there, is just thinking about, well, what's the accommodation space? How am I filling sediments into this area? Now, I warned you this is coming from basics, but this is how I interpret seismic. These are the processes I use. I sit there and think, well, what happened over time and how does it fill? And generally, sedimentation is relatively flat. Even if I've got cliniforms out on the shelf break, it's still relatively flat. And this is the host for all of these systems. And deltas build out and fill space. And so as I'm looking at this, I'm looking at these as being sets of deltas filling out my space, sitting on top of that. And if I've got thickness changes it's because I've got faults moving. This is from the Moray Firth in northeast Scotland, and here we've got a set of growth faults, and they're rotating around a ductile basement in here. And so what's happening is we're generating thickness in the hanging wall on the downthrown side, and the footwall is popping up, and we're generating accommodation space. And so if I'm going to put thickening across the fault, I can only thicken across the fault one way. Then finally, carbonates. They need sunlight. They just want to be in the sunlight. If they're not in the sunlight, they die. You can kill a coral reef by drowning it, getting it below 30 meters, it will drown, or you can cover it by sediments. But basically, if you see that you've got coral reefs in there, that to me, I'm sitting there going, interpreting my seismic, say, I need to be within 30 meters of the surface of the water surface. So this is something I use all the time, is those pinnacle reefs are my little things. If I'll see pinnacle reefs, how can I imagine them just having their heads in the sunlight? So where I live near here, I go into the Lachlan, and in the Abercrombie group, there's a whole series of these pinnacle reefs that go all the way up to Orange. And you can see these pinnacle reefs with turbidites around them. Now, the pinnacle reefs are obviously just keeping their heads in the sunlight. And then volcanoes and volcanics will just fill that space. So when I'm interpreting the seismic, I'm just trying to think about how the space is being filled in the basis, and then think about the faulting. So then finally we get erosion. We can erode these systems. This is actually Hutton's unconformity. This is down the borders of Scotland where I grew up as a kid. And this is actually his first unconformity where he saw this really significant change in dips. Look at that. That's a beautiful drawing. And this was the first understanding. This got religious people really upset. It was a very contentious diagram. And this is Sicca Point on the west coast of Scotland, again with this big angular unconformity. So tracking those unconformities, that will change thicknesses across faults. With erosion, it generally happens on land. It will happen in the marine environment, but generally erosion, if I see an eroded system, I know that I was out of the marine section. So this is actually, anyone who goes to Canberra, this is Lake George here. This is the highway going along here. And this was a single rain event. This same Abercrombie group eroded, and it's caught up on the fence, and it's about 45 centimeters of eroded fan scarp from one rainstorm. I drove to Canberra and drove back, and that's what was there in the afternoon. So that erosion comes through. Ken McClay's done some really nice stuff recently with some of his students looking at scarp retreat. And so I'm looking at those erosional events and how I pick my seismic in terms of that sequence. Now, we will get erosion in the marine environment. So if we are dealing with turbidites, we will get erosion. This is some work I've done with John Jong, who's a really good geologist at Nippon up in Malaysia. This is deepwater Sabah. And there you get these alisostromes, so these effectively submarine landslides, and you start to see channelized turbidites running down through this. So you will see some erosion, but it's not a peniplanation of the marine section. So when I see erosion, it tells me something about the environment. And then I need to start to think about my faults. Have I got sensible fault displacements? This is 90% of what I do in my fault seal analysis, is checking whether I've got sensible displacements. Footwall upthrown, hangwall downthrown. What's my displacement look like, and how can I chase that around? You can see with Strachi's cross section, if we actually go through and do a really simple restoration, and I restore that side to that side, he did a really good job. This is the first geologic section recorded, or the oldest geologic section, and it balances. No, they did a good job. There's no reason why we can't do it now. So fundamentally, just a little cartoon. If I have a fault, I have layers in here. If I move them up, they should be the same thickness either side. Now I can get growth. I've thickened this side. Oh, sorry. And in this case, my thickness is on the upthrown side. Now it could be inversion, but that's back to front. I need to think about why is it thicker on the footwall than in the hang wall. And if I see a cross section that looks like this, now what's going on here? Like, this looks to me like an error rather than being real geology. So tracking through those thicknesses is super important. So just another one to sit there and think about it. Just say to yourself, what do you think that looks like, that image there on the top right? Let's have a quick look. It's a bit of a trick. It's actually the streets of Lebanon, 1970s kitchen, and a Californian sky. But your brain starts to tell a story, even though we've got this blurry stuff. And we will do this with our geology all the time. You will look at your seismic and you will start to make up stories. And you make up stories in your head really quickly and you don't realize you're doing it. So this is why I really think this cognitive bias is a deep bit of how I pick seismic. How do I avoid cognitive bias? So there's a very quick example. Here's something in South Australia. This is the Cooper Basin. The mines department put out these set of sections. And the cool thing in doing seismic is you can do this vertical flattening. So you can effectively, that's the section here, and they've taken off this bit and they've just simply vertically sheared it up. So that layer becomes that layer. And then this becomes here. And so they've sheared them up. And by doing that, you sit there and you look at that and think about what sort of faulting that looks like. Okay, so this is the Della structure. This is one of the major oil fields in the Cooper Basin. This is the Gidjalpa field again. They've gone through and done this vertical shear, this vertical flattening. They've got themselves some normal faults sitting in through here. So these are them in here, the two structures on these ridges. 2020 Vintage Energies, prospectus. Again, they've got these, 60-degree dipping normal faults through the system. Well, no one's looked at Xiaowen Sun's work from the 1990s. And Thomas Flotman, who's a really good geomechanic up in Queensland, he's been saying this for years. The Cooper Basin is a whole set of fold and thrust belts. They've got these thrusts coming out of the base. They're not normal faults. So what happens is that people use a tool or they use a technique and they think they've got normal faults, and then they force everything to be normal faults. Whereas these are definitely reverse faults. If you get your depth conversion right, you'll start to see that these are actually a whole set of normal faults running, reverse faults running through the system. So it's super important to make sure that you avoid these anchoring biases. And we do this all the time. What's the largest mine in the country? What's the largest mine in the world? What's the steepest fault? All these things. That's how we judge ourselves. And we really need to go back and have a think about those sorts of biases. This is some really great work that Enrique Novoa, who's I worked with at Midland Valley, and he shows, this is from his PhD. This is some nice monoclines, and this is what happens. You take the monocline and you do vertical shear to it, which is the normal flattening that the geophysicists often do. You generate these sorts of structures. And he showed that instead, if you unfold this and you move it out to the right, then what happens is that's before, and this is the unfolded section moved out to the right. These continue to be sensible monoclines that propagate up through the structure instead of being really wonky. So it's super important to make sure you do that right. I end up using either Move or Lithotech for this. I used to work for Midland Valley and who make Move, and it's great for doing that. I also use something called Lithotech, which is made by Halliburton. I've got a business relationship with Halliburton for fault seal analysis, but both of them are horses for courses and really useful bits of software. Having said that, there's a lot you can do with pencil and paper. Ken in this little book in here, he says always take your map measure and measure the line length using a wheel or a string. You can do it that way. You can do it in PowerPoint. So just to give an example of what you can do with seismic interpretation in PowerPoint, this is ACARP, the coal industry group, looking at the supermodel as a basin. This is looking at the Bowen Basin and the tertiary sitting on top of the coal measures. So here's one of the cross sections. So you can start to see here, we've got ourselves a cross section. First thing I'm hoping you're realizing is it's in two-way time, and we should be careful about doing any depth. We should be careful about doing any interpretation in here. But immediately I'm starting to look at this and go, oh, what's going on here? So it's in two-way time. In PowerPoint, I can just go through and I can color up the layers. And you can work on Seismic in PowerPoint, no problem at all. And you can start to see, as soon as I color up my layers and I start to fill them up, you can start to see, we've got some thickness issues in here and what's in here, because my interpretation is not in there. So, and one of the real tricks with seismic interpretation is tying all these disparate bits of information together. They mark the fault tips in here, and I've got this tip in here. I've actually got probably got a propagation fold in here. So if I start to then take that and just put them as blocks, if they're colored fill blocks in PowerPoint, you can then start to move these around, and you can just move them around by hand in PowerPoint. So then you can start to say, well, look, I can then move this fault down. That sorts that one. I can start to see where I've got some issues in here, and then I can move this fault in here, and you can see as I move it and rotate it, I've got real space issues on the fault here. There's something wrong with this geometry, and we could see that in that there were thickness issues in here, and this fault propagation fold, I've got something going on in here. Well, I'd be tempted to say, well, look, that's my eroded section in there, and that's what it should look like. Now, if I was doing that in Lithotech, that's what it looks like in depth converted. It's a really straightforward process to do the depth conversion, but it's worth doing. That's what it looks like, depth converted. That's what my fault propagation fold looks like, uneroded. And that's what it looks like 3 times vertical exaggeration. You can see immediately it all starts to look wonky. It's super important to get this vertical exaggeration right. And then that's what it would be balanced in depth. So it's important, super please try and get your geophysicists to get you to help work in depth. Don't work in time. Watch out for the units and the vertical exaggeration. You will stumble across this. Always check that stuff. Yeah, and we all make mistakes. My mantra as a geologist is the only thing I know is I'm wrong. And my job is to try and work out how I'm wrong and describe how I'm wrong. So I'm trying to be roughly right rather than precisely wrong. So I'll just leave you with one of my favorite cognitive bias. I'm sort of collecting them now. This is the IKEA effect. And you go to IKEA, and I built my office here during COVID, and I got all this IKEA, and I put it out and I assembled it, and I had my 12-year-old daughter helping me assemble it, and we did it wrong 3 times. We eventually got it together, got it right, having finally read the instructions properly. And I was really happy with it, and we're both really happy, and we're proud, but and I sat there and thought, well, this is really good. And the IKEA effect is you sit there and say, well, hey, I know this is really crappy timber. There's no skill in this, but I'm really happy and proud that I've made it. And this is what I find I'm doing with my seismic interpretation a lot of the time. If it's easy to interpret, they'll get a geophysicist. If it's difficult to interpret, they'll get a structural geologist. And so we always get the crappiest bits of data. But I tell you what, when you get it and you get it together, you're so proud of it. You think that's the best thing ever. But you have to remind yourself the whole time, you only got this job because it was a really crappy bit of data in the first place. So I hope you've got some ideas about how to deal with seismic, and if you've got any questions, go for it.
That was awesome.